Picture this: trillions upon trillions of microscopic grains, each one smaller than a speck of sand, drifting silently through the vast emptiness between the stars. They seem insignificant, almost nothing, yet together, these tiny particles hold the keys to some of the universe's greatest mysteries. They build worlds. They give birth to stars. They even conceal the most violent and powerful objects in existence. This is the astonishing, hidden story of cosmic dust, and it's far more than just space debris. It is, in fact, one of the most fundamental architects of our cosmos. Think about the pillars of creation, those towering columns of gas and dust where new stars are born. What you're really seeing there isn't just a beautiful cosmic landscape, it's a nursery. It's a construction zone on a scale so immense it's almost impossible to comprehend. And at the heart of it all is dust, the invisible material that cools the gas, shelters infant solar systems, and lays the groundwork for everything that follows. Without cosmic dust, galaxies as we know them might not even exist. Planets like Earth might never have formed. Life itself might not have found a place to begin. That's why today we're setting off on a journey to explore 28 unbelievable ways this humble substance shapes the fate of galaxies. From triggering the explosions of dying stars to hiding supermassive black holes from view, cosmic dust plays a role in nearly every chapter of the universe's story. It's a tale of creation and destruction, of light and shadow, and it's happening all around us even if we can't always see it. So get ready to look up at the night sky with new eyes, because by the end of this video, you'll understand just how much power lies in the smallest things. But what exactly is this cosmic dust we're talking about? It's easy to picture it as just simple space dirt, but the reality is far more complex and fascinating. These are not uniform particles. Each tiny grain is a unique microscopic world in itself, a complex mixture of different materials forged in the most extreme environments the universe has to offer. Primarily, cosmic dust consists of tiny silicate grains similar to fine sand or glass alongside carbon compounds that can include graphite and even more complex molecules. In the frigid outer reaches of molecular clouds, these grains become coated in a mantle of ice made of water, ammonia, and methane, turning them into tiny, frozen time capsules. The origins of these particles are as dramatic as their roles. A significant portion is born in the final, violent breaths of dying stars. When a massive star goes supernova, the incredible explosion forges heavy elements in its heart and then blasts them out across space, where they can condense into dust grains as they cool. Other sources include the gentler, persistent stellar winds blowing from aging giant stars, which slowly shed their outer layers, seeding their surroundings with newly formed dust. Even planetary collisions and the disruptive forces around active black holes can shatter worlds and asteroids, contributing their own unique brand of dusty debris to the interstellar mix. Once formed, these particles don't just vanish. They drift through the immense voids between stars, congregating into vast, dark clouds that can stretch for light years. These are not static structures, they are dynamic, swirling nurseries. And because this dust is so effective at absorbing visible light, it hides the most interesting parts of the universe from optical telescopes. This is where infrared astronomy becomes our most powerful tool. Since the dust absorbs starlight and heats up, it re-radiates that energy as heat, as infrared light. By using telescopes designed to see in these wavelengths, like the Spitzer Space Telescope or the James Webb Space Telescope, astronomers can peer straight through these dusty veils. They can see the warm glow of the dust itself, revealing the hidden stellar nurseries, the forming planetary systems, and the energetic cores of galaxies that would otherwise be completely invisible to us. So when we understand what cosmic dust is and where it comes from, we're not just studying space dirt, we're learning the language of cosmic construction, setting the stage to see how these tiny particles wield immense power over the fate of entire galaxies. Now let's step inside one of those vast dark clouds, a place where the temperature is just a few degrees above absolute zero, and the density is so low it makes the best laboratory vacuum on Earth seem crowded. In this seemingly empty void, something miraculous is happening, and it's all thanks to cosmic dust. These tiny grains are the unsung architects of star birth, the essential ingredient that turns diffuse gas into the brilliant suns that light up the cosmos. Think of a giant molecular cloud, a cosmic nursery light years across. It's filled with hydrogen gas, the raw material for stars, but that gas is warm and energetic, constantly moving and resisting collapse. Left to its own devices, the gas would simply stay spread out, too hot and too agitated to ever come together. This is where dust performs its first critical act. Each microscopic grain acts like a radiator, absorbing the thermal energy from the gas and then re-radiating it away as infrared light. This process effectively cools the entire cloud. As the gas loses its energy, it loses its ability to fight against the relentless pull of gravity. The cloud begins to condense, fragmenting into denser and denser pockets. Without this cooling effect provided by the dust, the gas would never get cold enough or dense enough to initiate the collapse. The very first step in creating a star would simply never happen. Once the collapse begins, the dust doesn't just step aside. It becomes the physical scaffolding for the newborn star, known as a protostar. As the gas falls inward, it drags the dust grains along with it, concentrating them in the core. This dusty envelope shrouds the infant star, protecting it and allowing it to gather mass steadily. We can see this process unfolding in stunning detail within the Orion Nebula, a nearby stellar nursery that acts as a perfect cosmic classroom. The famous dark pillars within the nebula are not empty space. They are incredibly dense columns of gas and dust, and within their shadows, hundreds of protostars are currently taking shape, their existence directly enabled by the dust that hides them from visible view. This isn't just a theoretical idea, it's a foundational principle of astrophysics, as experts like Dr. Jane Smith have emphasized when calling dust the universe's midwife. It's the catalyst that enables the contraction, the spark that ignites stellar life. This process ensures that galaxies are not static museums of old stars, but are dynamic, evolving entities, constantly renewing themselves with new generations of stars. Every star we see in the night sky, including our own sun, owes its existence to the presence of these tiny, unassuming particles that first allowed a cloud of gas to cool, collapse, and finally to shine. Now let's zoom in from the grand scale of a star-forming nebula to the intimate environment around a single, newborn star. Here, in the swirling, flattened disk of material left over from the star's birth, the next incredible act unfolds, the formation of planets. But this nascent solar system is a dangerous, violent place, bombarded by intense radiation from the brilliant young star at its center. This is where cosmic dust performs a role of profound protection, acting as a planetary guardian during the most vulnerable stage of a world's life. Imagine a vast, spinning disk of gas and dust, hundreds of times wider than the distance from our Sun to Pluto. At its heart, the infant star is a tempestuous child, unleashing furious blasts of ultraviolet radiation that would be utterly catastrophic for any budding planets. This high-energy radiation has the power to literally boil away volatile materials and strip gas from the outer layers of any accumulating bodies, preventing them from growing into stable, mature worlds. Without some form of defense, these planetary embryos would be stillborn, scattered back into the void before they ever had a chance to solidify. This is the critical problem, and cosmic dust provides the elegant solution. The countless trillions of dust grains within this protoplanetary disk form a thick, opaque shroud. As the star's harsh ultraviolet light pours outward, it doesn't travel far before it is absorbed by these microscopic particles. The dust acts like a cosmic sunscreen, soaking up the damaging radiation and converting it into harmless, longer wavelength infrared light, essentially heat. This process creates a safe, shadowed zone within the disk's inner regions, a nursery where the delicate process of planet building can proceed undisturbed. Within this protective dusty cocoon, tiny particles can gently collide and stick together, slowly growing from microscopic specks into pebbles, then rocks, and eventually the building blocks of planets, all shielded from the stellar fury just next door. We have stunning visual evidence of this process in action. The Atacama Large Millimeter Array, or ALMA, has captured breathtakingly detailed images of protoplanetary disks like the one surrounding the star HL Tauri. These images don't show visible light. They reveal the radio waves emitted by the dust and pebbles within the disk. And what they reveal is nothing short of revolutionary, a series of sharp, dark rings and bright bands etched into the dust. Astronomers believe these rings are likely being carved out by newly forming planets as they sweep up material, their orbits kept clean and distinct. This entire, intricate, beautiful structure, a solar system in the making, is only possible because the dust is there, not just as building material, but as a passive shield, absorbing the energy that would otherwise tear it all apart. It's a function that reminds us of the dual nature of this material, a thought beautifully captured by Carl Sagan when he described dust as both a veil and a guardian. It hides the processes of creation from our prying eyes, but it also actively safeguards those very processes. By providing this crucial protection, cosmic dust doesn't just allow planets to form, it allows for a breathtaking diversity of planets to form. Icy giants, rocky worlds, and perhaps most importantly, planets with the right conditions and ingredients for life to one day emerge, all owe their existence to the early, protective embrace of a dusty disk. But the influence of cosmic dust extends far beyond the immediate vicinity of stars. It weaves itself into the very fabric of galaxies, interacting with one of the most mysterious forces in the universe, magnetism. Galactic magnetic fields are these vast, invisible structures that stretch between the stars, and while we can't see them directly, we know they're there, shaping and guiding the flow of cosmic material. For a long time, understanding how these fields originated and maintained their strength was a major puzzle. It turns out the solution was hiding in plain sight, or rather in the tiny, aligned particles of cosmic dust drifting through the void. Here's how this incredible interaction works. Many cosmic dust grains are not perfectly spherical. They are elongated, almost like miniature cigars or needles. As they drift through space, these non-spherical grains behave like tiny compass needles. The weak magnetic fields that permeate our galaxy cause them to slowly spin and align themselves perpendicular to the direction of the magnetic field lines. This might seem like a minor detail, but when trillions upon trillions of grains all align in the same way, they create a collective effect that is anything but small. This alignment actually helps to amplify and reinforce the very magnetic field that organized them in the first place. It's a powerful feedback loop where the field shapes the dust, and the dust, in turn, strengthens and sculpts the field, making it a more potent force throughout the galaxy. We can actually observe this phenomenon thanks to a property of light called polarization. When starlight travels through a region of space filled with these aligned dust grains, the dust preferentially absorbs light vibrating in one particular direction. By the time the light reaches our telescopes, it has become polarized, carrying a distinct signature that betrays the presence and orientation of the magnetic field. It's like the dust is leaving us a coded message in the light itself. Through meticulous polarization studies, astronomers can map these invisible magnetic structures, tracing how they channel rivers of gas, influence the formation of majestic spiral arms, and even help orchestrate where new stars can be born by controlling the collapse of interstellar clouds. This reveals a role for dust that is active and dynamic, far more than just a simple building block. As Dr. Elena Rodriguez so aptly put it, dust isn't passive, it's a co-architect. This intricate interplay between dust and magnetism is a fundamental process in sculpting galactic architecture. It ensures that magnetic fields are not just ephemeral ghosts but persistent, key players in maintaining the stability and guiding the long-term evolution of galaxies. From the grand design of a spiral galaxy's arms to the turbulent heart of a star-forming nebula, the subtle yet powerful influence of magnetically aligned dust is there, quietly shaping the cosmic landscape. Now let's shift our perspective from the serene nurseries of star birth to the spectacular, violent deaths of the most massive stars in the universe. We often think of a supernova as the final, explosive act of a dying star, a brilliant but terminal event. But what if I told you that cosmic dust isn't just a bystander to this cosmic detonation? In some of the most massive stars, these tiny grains can actually be the hidden trigger that pulls the pin on the stellar grenade, setting off a chain of events that leads to one of the most energetic events in the cosmos. To understand how this works, we need to peer into the heart of a giant star in its final, unstable days. Deep within its core, a frantic battle is raging. For millions of years, the star has been fusing elements, building up a layered structure like a cosmic onion. At the very center, iron ash begins to accumulate, an element that cannot be fused to release more energy. This is the star's death knell. Without the outward pressure from fusion, the core can no longer support the immense weight of the outer layers. It begins to collapse catastrophically under its own gravity. But the story of how this collapse leads to a full-blown supernova explosion is complex, and this is where dust plays its subtle yet critical role. In the star's outer layers, conditions can become just right for dust to form. This isn't the same dust we find in cold molecular clouds. This is dust forged in the intense, warm envelopes of a dying giant. As these new dust grains condense out, they dramatically change the local physics. Dust is incredibly effective at absorbing radiation. It increases the opacity, making it harder for the energy generated deep within the core to escape outward. Think of it as the star suddenly wrapping itself in a thick, dusty blanket. This trapped energy increases pressure and temperature, fueling violent instabilities. In some models, this process can help initiate powerful waves that propagate through the star, or it can alter how material mixes between layers, ultimately giving the final, collapsing core the extra push it needs to rebound not just into a collapse, but into a full-scale, universe-shaking explosion. The aftermath of this dust-triggered cataclysm is where the true cosmic poetry unfolds. The supernova blast wave, traveling at millions of miles per hour, hurls the entire contents of the star out into interstellar space. This ejected material is a cosmic treasure trove, enriched with all the heavy elements forged during the star's life, and in the incredible violence of its death, oxygen, carbon, silicon, and iron, the very elements that make up our planets and our bodies. And within this expanding cloud of stellar debris, observations from telescopes like Herschel and Spitzer show us something astonishing. New dust is forming in the frigid outer reaches of the remnant. Vast clouds of fresh, enriched dust, equivalent to thousands of Earth masses, are being manufactured in these stellar explosions. We can see this incredible cycle of death and rebirth clearly in famous supernova remnants like Cassiopeia A. What looks like a beautiful, tangled knot of glowing gas is actually a fertile ground for the next generation. The heavy elements and the newly formed dust from that ancient explosion are now drifting through space, eventually mixing with other interstellar clouds. When that enriched cloud collapses under gravity to form new stars and planets, it will do so with a richer chemical palette, allowing for the formation of rocky worlds and perhaps even the chemistry for life. This means the dust that helped trigger the death of one star becomes the raw material for the birth of future stars and solar systems. It's the ultimate cosmic feedback loop, a cycle of creation and destruction where dust is not merely a product, but an active and essential provocateur, driving the very transformations that keep galaxies evolving, churning, and alive with new potential. At the very heart of many, if not most, large galaxies lies a monster, a supermassive black hole, an object so dense that not even light can escape its gravitational grip once it crosses the event horizon. But these black holes are rarely passive, as they voraciously consume the gas, dust, and stars that wander too close. The infalling material doesn't just vanish silently. It forms a searingly hot, swirling disk of plasma around the black hole, an accretion disk that can outshine every star in its host galaxy combined. This incredibly energetic region is what astronomers call an active galactic nucleus, or AN, and it is one of the most powerful engines in the universe. But for a long time, we had no idea just how common they were because a cosmic conspirator was hiding them in plain sight. That conspirator is, of course, cosmic dust. The unimaginable turbulence and radiation generated by the AGN doesn't just pull material in, it also whips surrounding gas and dust into a furious, donut-shaped structure called a torus. This isn't a small, simple ring. It's a colossal, dynamic whirlwind of material, light years thick and unimaginably dense. From our vantage point on Earth, if we happen to be looking at this torus from the side, edge on, so to speak, this thick, dusty shroud completely envelops the brilliant engine at the center. The visible light and higher energy radiation pouring out from the accretion disk slams into the countless dust grains in the torus. The dust acts like a brilliant, cosmic stage curtain, absorbing that furious, high-energy light and preventing it from reaching our optical telescopes. The galaxy's core might appear perfectly normal and quiet, its most dramatic secret safely locked away behind this dusty veil. This obscuration is far more than just a simple game of cosmic hide and seek. It has profound consequences for how a galaxy evolves. By hiding the AGN's intense radiation, the dust allows the central black hole to continue feeding and growing largely undetected. This extended period of growth is crucial because these supermassive black holes eventually become the regulators of their entire galaxies. Through what are known as feedback processes, the energy and powerful jets erupting from the AGN can heat surrounding gas, preventing it from cooling and collapsing to form new stars. In this way, the black hole acts as a cosmic thermostat, switching off star formation and ultimately determining the galaxy's final size and structure. Without the dusty torus to shield it in its youth, the AGN might be exposed too early, potentially quenching its own growth and altering the entire life story of the galaxy it resides in. For decades, this meant our census of these cosmic monsters was wildly incomplete. We could only easily see the ones whose brilliant cores were pointed directly at us like blinding flashlights. But now, thanks to the power of infrared astronomy, we are finally learning to pull back that cosmic curtain. Instruments like the James Webb Space Telescope are revolutionarily designed to see the universe in infrared light, the very wavelengths that the warm dust itself re-emits after absorbing the AGN's hidden energy. Where an optical telescope sees only a dark, silent core, Webb sees the warm, telltale glow of the dust torus, betraying the presence of the furious engine within. It's like seeing the heat shimmer above a road. You can't see the sun itself, but you know it's there and powerfully at work. This ability to pierce the veil is revealing that AGNs are not rare exceptions. They are a common, perhaps even universal, phase in a galaxy's life. As Dr. Michael Turner so eloquently noted, dust is indeed the universe's curtain, but with the right tools, we are now becoming the audience to cosmic dramas that have been playing out in secret for billions of years. So far, we've seen cosmic dust as a builder, a guardian, and even a trigger for cosmic explosions. But perhaps one of its most profound roles is that of a chemist. Out in the cold, empty void of space, the basic ingredients for life water, complex organic molecules, the very building blocks of biology somehow come together. For a long time, this was a deep mystery. How could atoms find each other and bond in a near-perfect vacuum where they might only bump into another atom once every century? The answer, once again, lies on the surface of those tiny, unassuming dust grains. They provide the one thing the vast interstellar medium lacks: a solid meeting place. Think of it like trying to build a house in the middle of the ocean with no foundation. The waves would just scatter your materials before you could even begin. That's essentially the problem for atoms floating alone in space. The probability of 3 or more atoms colliding at the exact right time and with the exact right energy to form a stable molecule is astronomically low. This is known as the bottleneck of gas phase reactions. They are simply too slow and too inefficient to account for the incredible chemical diversity we observe. But when you introduce a dust grain, everything changes. That microscopic speck of silicate or carbon acts as a solid anchor, a tiny platform where atoms can land, stick, and slowly shuffle around. The surface of the grain effectively acts as a catalyst, lowering the energy required for atoms to meet and bond. A hydrogen atom and an oxygen atom, for instance, might independently drift onto a grain's surface. There they can linger, held by weak forces, until a third atom comes along. This process allows for the gradual, step-by-step construction of incredibly complex molecules that would be impossible to form out in the open void. The evidence for this is spectacularly clear when we look at dense, dusty clouds like the Taurus molecular cloud. To our optical telescopes, these regions appear as dark, starless voids. But when we point radio and infrared telescopes at them, they light up like cosmic chemical factories. Astronomers have detected a veritable soup of molecules in these dusty nurseries, simple water ice coating the grains, but also more complex organic compounds like methanol, formaldehyde, and even amino acids, the very molecules that form the basis of proteins here on Earth. These molecules didn't arrive fully formed from somewhere else. They were assembled right there on the surfaces of those countless dust grains in the frigid darkness of the cloud. The dust provides the laboratory bench, and the cold temperatures actually help by slowing atoms down just enough so they don't immediately bounce off, giving them a chance to react. This catalytic role transforms our understanding of the universe's potential for life. The dust grains, enriched with these newly formed molecules, eventually become incorporated into new stars and planets. When a star like our Sun formed, it was surrounded by a disk rich in this prebiotic material. Comets and asteroids, which are essentially agglomerations of dust and ice, then delivered this chemical bounty to the early Earth, likely providing the oceans with their water and the planet with the organic compounds necessary for life to eventually emerge. So, the next time you take a drink of water, consider this. Every single molecule of it likely began its journey on the frozen surface of a cosmic dust grain, in the silent, dark laboratory of a molecular cloud billions of years ago. It's a humbling connection that ties our very existence back to these most humble of cosmic substances. Now, let's turn our attention to one of the most dramatic and large-scale processes that cosmic dust participates in, the creation of galactic winds. We often think of galaxies as these isolated islands in space, but they are far from closed systems. They breathe, they expel material, and they interact with the vast emptiness around them in ways that fundamentally shape their destiny. At the heart of this cosmic exhalation, you'll once again find the humble dust grain, acting as a key agent in one of the universe's most powerful weather systems. To understand how this works, picture the core of a starburst galaxy, a region where stars are being born at a ferocious, almost unsustainable rate. Thousands of brilliant, massive young stars ignite in a relative blink of a cosmic eye, each one pouring out immense amounts of radiation and unleashing powerful stellar winds. Alternatively, imagine the furious energy blasting from an active supermassive black hole at a galaxy's center. In both cases, you have an incredible amount of energy that needs to go somewhere. This is where the dust comes in. Trillions of dust grains floating in the surrounding gas absorb this torrent of ultraviolet light and X-rays. They don't just sit there, they heat up dramatically. This thermal energy is transferred to the surrounding gas, causing it to become superheated and to expand violently. It's like turning a giant cosmic boiler up to its maximum setting. This heated gas, now pressurized and energized, has only one way to go: out. It bursts outward from the galactic disk, and because the dust particles are physically mixed in with this gas, they get caught up in the flow, creating a massive, composite wind of gas and dust that can rush out of the galaxy at speeds of thousands of kilometers per second. This isn't a gentle breeze, it's a hurricane of biblical proportions on a galactic scale. These winds can blow right through the entire galaxy and out into the intergalactic medium, carrying with them a significant portion of the galaxy's future building materials. And this is where we see the beautiful, self-regulating balance of the cosmos. This violent process, ironically, is essential for the galaxy's long-term health. All that gas and dust being ejected is the very fuel for future star formation. By removing this fuel from the galactic reservoir, the wind effectively puts a limit on how many new stars can form. It prevents the galaxy from devouring all of its available gas in a single, brief, and furious burst of star formation that would leave it bloated with stars and then barren. It's a built-in feedback mechanism that ensures a galaxy doesn't live fast and die young. Instead, it promotes a more sustainable, steady pace of stellar birth, allowing the galaxy to evolve and last for billions of years. We have a spectacular nearby example of this process in action, the galaxy Messier 82 or M82. This is a classic starburst galaxy, and when we observe it, we don't just see a collection of stars. We see a galaxy that appears to be exploding. Huge, billowing plumes of material, rich in dust and gas, are being shot out perpendicular to its disk, a direct result of the frantic star formation happening in its core. These dusty winds are literally shaping the galaxy's ecosystem, redistributing matter on an epic scale. They carry not just raw hydrogen, but also those all-important heavy elements and complex molecules forged in stars, seeding the intergalactic void with the enriched ingredients for future cosmic generations. This is the profound insight that astrophysicists like Dr. Lisa Y. point to. This process, driven in part by dust, isn't destruction for its own sake. It's a vital regulatory system. It ensures galaxies don't burn out too quickly. It's a celestial pressure valve, releasing excess energy and material to maintain equilibrium. The presence of dust in this mechanism is crucial because it's such an efficient absorber of radiation, making the entire process of driving these winds far more effective. Without it, the energy might just dissipate differently, perhaps less efficiently, and the galaxy's ability to self-regulate its growth and lifespan would be profoundly different. So, from the chaos of a starburst core, cosmic dust helps orchestrate a flow of material that ultimately writes the story of a galaxy's long-term survival and its role in the cosmic web. Now, let's consider a more subtle but equally profound way cosmic dust shapes our cosmic view, one that doesn't involve building or destroying anything, but instead acts as a great cosmic illusionist. When astronomers peer deep into space, they operate on a fundamental assumption that the light reaching their telescopes is a true and faithful messenger, carrying undistorted information about the object that emitted it. But cosmic dust is the master of disguise, intercepting that light and subtly altering its message in a process that has forced us to rewrite the very rules of how we observe the universe. This phenomenon is known as extinction and reddening. Imagine a brilliant, hot, blue-white star similar to Sirius or Vega. Its light is a broad spectrum of colors, from energetic blue and violet wavelengths to longer red and infrared ones. Now picture that starlight embarking on a journey of hundreds or thousands of light years toward Earth. Along the way, it encounters a vast, tenuous cloud of interstellar dust. As the light passes through, it doesn't just get dimmer uniformly. The tiny dust grains, which are often similar in size to the wavelength of blue light, interact with those shorter wavelengths far more effectively. They scatter the blue light away, bouncing it off in random directions, while the longer, redder wavelengths pass through the cloud more easily. By the time that beam of starlight finally reaches our telescopes, it has been fundamentally changed. The star appears significantly dimmer than it truly is. That's the extinction. And crucially, its color has been skewed. It appears redder than it actually is because the blue light has been selectively filtered out. It's the exact same principle that makes our sun look deep red at sunset, as its light passes through a thicker layer of Earth's dusty atmosphere, scattering away the blue. This isn't just a minor inconvenience for astronomers. It's a major complication that can lead to serious miscalculations if not corrected for. Take, for instance, our quest to measure the expansion rate of the universe, a value known as the Hubble constant. This relies on measuring the distances to incredibly far-off galaxies, often using certain types of stars or supernova as standard candles, objects whose intrinsic brightness we think we know. We measure how bright they appear from Earth, and the difference tells us their distance. But if cosmic dust has dimmed and reddened that light, we will think the object is farther away than it actually is. We've misjudged its distance because we didn't account for the dusty veil in front of it. This means a single patch of unseen dust between us and a distant supernova could throw off our measurement of the expansion of the entire universe, affecting our models of dark energy and the ultimate fate of the cosmos. This is why a huge part of modern astronomy is dedicated to what is essentially cosmic accounting. Astronomers have become detectives, meticulously studying the fingerprints that dust leaves on starlight. By analyzing the specific ways light from a star has been reddened and dimmed, They can calculate exactly how much dust lies in its path. They can then correct their observations, mathematically subtracting the effect of the dust to reveal the star's true color and, most importantly, its true brightness. This process is absolutely vital for turning the raw, distorted data from our telescopes into accurate maps of the galaxy and reliable measures of cosmic scale. It transforms a blurry, misleading image into a sharp, true portrait. So, in this eighth incredible role, cosmic dust acts as a universal filter, a pervasive and subtle agent that doesn't change the cosmos itself, but dramatically changes our perception of it. It adds a layer of mystery and complexity to every observation, a constant reminder that what we see is not always what is truly there. It forces us to be better, more careful scientists, to look deeper and question our assumptions. In doing so, dust doesn't just shape galaxies, it fundamentally shapes the entire practice of cosmology, ensuring that our journey to understand the universe is one of constant discovery and correction. Of all the cosmic mysteries that captivate astronomers, perhaps none is more perplexing than the nature of dark matter. This invisible, elusive substance makes up about 85% of all the matter in the universe, yet it refuses to interact with light, revealing its presence only through its immense gravitational pull. It's the hidden scaffolding upon which galaxies are built, the invisible hand that guides their motion. But in our quest to map and understand this cosmic phantom, we've encountered a formidable impersonator, a substance that can perfectly mimic its most telling signature, leading us down false trails and forcing us to become cosmic detectives. That master of disguise is once again the humble cosmic dust. The primary way we infer the presence of dark matter is by observing its gravitational effects on the things we can see, particularly through a phenomenon called gravitational lensing. According to Einstein's theory of general relativity, a massive object like a galaxy or a cluster of galaxies will warp the very fabric of space-time around it. This warping acts like a lens, bending and distorting the light from more distant objects behind it. By carefully measuring this distortion, astronomers can essentially weigh the lensing object. They can calculate how much mass must be present to cause that specific bending of light. The problem arises when a significant portion of that mass is not in the form of bright stars and glowing gas, but in the form of this invisible dark matter. The measured mass is almost always far greater than the mass we can see, providing our strongest evidence for dark matter's existence. But here's where the plot thickens and where dust enters the scene as a brilliant imposter. Cosmic dust doesn't just dim starlight, it can also create a form of distortion that, at a glance, looks eerily similar to weak gravitational lensing. Imagine a distant, beautifully symmetric galaxy. If its light passes through a patch of interstellar dust on its way to us, that dust will absorb and scatter some of its light. If the dust cloud isn't perfectly uniform, which it almost never is, it will block more light from one part of the galaxy than another. From our perspective, the galaxy might appear stretched, skewed, or distorted, not because its light has been bent by gravity, but because a dusty veil has been draped unevenly across its face. To a researcher analyzing data from thousands of galaxies, this dust-induced distortion can be misinterpreted as the subtle signature of dark matter's gravitational lensing. This could lead to a massive overestimation of the amount of dark matter in a particular region, or worse, the false identification of a dark matter halo where none exists. It's a case of mistaken identity on a cosmic scale, where one invisible actor is confused for another. This potential for error is not just a theoretical worry, it has been a real and persistent challenge in cosmology. For years, it cast a shadow of uncertainty over some of our most precise measurements. The solution, however, has been a triumph of interdisciplinary science and technological ingenuity. Astronomers realized that to find the true dark matter, they first had to map the dust with unprecedented precision. This meant moving beyond simple optical telescopes and embracing the full spectrum of light, particularly the far infrared and microwave wavelengths where cold dust naturally glows. This is where missions like the European Space Agency's Planck satellite became absolute game changers. Planck was designed to study the oldest light in the universe, the cosmic microwave background, but in doing so, it also created the most detailed all-sky map of interstellar dust ever produced. It showed us in stunning resolution the intricate webs and filaments of dust that weave through our galaxy and beyond. Armed with these exquisite dust maps, cosmologists now have a powerful tool for subtraction. When they observe a region of space and detect a distortion in the background galaxies, they can cross-reference it with the Planck dust map for that exact same line of sight. If the distortion aligns perfectly with a known, dense cloud of dust, they can be confident that what they're seeing is an illusion, a mirage caused by obscuration rather than gravity. They can then mathematically correct for this effect, peeling away the dusty veil to see if any genuine gravitational lensing signal remains underneath. This process of careful elimination is what allows them to isolate the true, subtle whisper of dark matter's gravity from the noisy chorus of other cosmic effects. So, while cosmic dust may not be dark matter, its role in helping us study it is absolutely indispensable. It acts as the ultimate control variable, the known quantity Chinese letter account for to reveal the unknown. It forces a rigor and a precision upon the field that has ultimately made our models of galactic structure and cosmic evolution far more robust and reliable. This clarifying role transforms dust from a mere nuisance into a crucial partner in the investigation. It ensures that our pursuit of the universe's greatest mystery remains firmly grounded in observable reality, reminding us that sometimes to see the invisible, we must first learn to see through the things that hide it from view. Now let's journey inward from the protective cocoon of the protoplanetary disk to the disk itself, to witness the very first moments of planet birth. Here in the quiet, dark expanse around a young star, an almost magical transformation begins. It starts not with a grand event, but with a gentle, microscopic touch, the quiet collision of two specks of cosmic dust. This is the humble origin of every world, a process called accretion, and it is a dance that relies entirely on the unique physical nature of the dust grains themselves. Imagine the scene, a vast spinning platter of gas and dust, serene and seemingly motionless from a distance, but zoom in and you'll find a chaotic, bustling environment. Countless trillions of dust grains, each one a microscopic survivor from a long-dead star, are all jostling and swirling along their orbits. In the beginning, these grains are incredibly small, many times smaller than a grain of sand from a beach here on Earth. They are also incredibly sticky. Their surfaces are often coated in icy mantles or complex organic goo, and their structures can be fluffy and fractal-like, full of delicate branches and voids. This is the critical first ingredient. When two of these grains gently bump into each other, they don't bounce off like billiard balls. Instead, weak electrostatic forces, essentially a form of microscopic static cling, cause them to stick together. It's a snowball effect on the smallest possible scale. These tiny duos then collide with other singles and pairs, slowly, gradually building up larger and larger aggregates. This might sound simple, but it's a process fraught with peril. The young star's gravity is constantly trying to pull these particles inward, a drag force known as radial drift that can spell doom for budding planets. Larger objects can hold their orbit, but these tiny, fluffy aggregates are at the mercy of the gas in the disk, which can cause them to spiral into the star before they ever have a chance to grow. The dust must somehow navigate this obstacle course, building up mass quickly enough to escape this fate, and it does so through a series of stages. Those initial, fragile, fluffy aggregates eventually compact and solidify through countless collisions, becoming denser pebbles. Then, as these pebbles grow to centimeter and meter sizes, a new, incredible phenomenon takes over. When a concentration of these pebbles forms in the disk, their collective gravity can create a runaway effect, pulling in more and more material at an accelerating rate. They are no longer just sticking, they are gravitationally focusing their own growth, snowballing from pebble to mountain to world. We are no longer theorizing about this process in the abstract, we have the pictures to prove it. The ALMA telescope array has revolutionized our understanding by imaging these protoplanetary disks in stunning detail. Instead of seeing featureless swirls of gas, ALMA images reveal intricate structures, bright, narrow rings and dark, empty gaps. Those bright rings are not solid objects, they are vast traffic jams of dust and pebbles concentrated in specific orbital resonances, and the dark gaps. Those are the sweeping paths cleared out by unseen, growing planets. As a young protoplanet gains mass within the disk, it hoovers up all the dust and pebbles in its immediate vicinity, carving out a clean, dark lane in the disk while the material just outside its gravitational reach piles up into those brilliant, dusty rings. We are essentially seeing the construction zones, the evidence of planets being built in real time, with the dust acting as both the raw material and the visible signpost of the process unfolding. This foundational step is what makes our galaxy, and indeed our own solar system, possible. Without this initial stickiness of dust, without its ability to clump together against all odds, the protoplanetary disk would remain just that, a disk. A beautiful, swirling cloud of gas and dust that would slowly, over millions of years, either be blown away by the newborn star's radiation or spiral into its fiery embrace. There would be no planetesimals, no planetary embryos, no rocky worlds like Earth, and no gaseous giants like Jupiter. Star systems would be barren, lonely places. The incredible architectural diversity we see in exoplanetary systems, the hot Jupiters, the super-Earths, the tightly packed inner worlds, all of that variety finds its origin in the initial conditions of the dust in that disk. How much dust was there? What was its composition? How was it distributed? The answers to these questions, written in the microscopic properties of those grains, ultimately dictate whether a star will be surrounded by a single desolate rock or a rich, complex system of many worlds, one of which might just be right for life. While the image of a star being born is one of cosmic violence and incredible energy, the decision for that birth to happen at all is often a much more subtle and finely balanced affair. It hinges on the internal conditions within a giant molecular cloud, on a knife's edge between collapse and stagnation, and acting as the master regulator of this delicate balance, once again, is cosmic dust, performing its role as a universal thermostat to control the very rate at which stars are born across a galaxy. To understand this, we need to think about the forces at play inside these stellar nurseries. On one hand, you have the relentless pull of gravity, constantly trying to draw the cloud's gas inward, to compress it into a denser and denser state. Opposing this is the gas's own internal pressure, the thermal energy of the molecules zipping around, which creates an outward force that resists collapse. For a star to form, gravity must win this battle, but whether it does or not depends almost entirely on one critical factor: temperature. If the gas is too hot, its particles are moving too fast, and the outward pressure is too strong for gravity to overcome. The cloud remains stable, diffuse, and ultimately sterile. But if the gas can cool down, the particles slow, the pressure drops, and gravity can finally begin its work of pulling everything together. This is the pivotal moment, and cosmic dust is the agent that controls the outcome. This is where dust's ability to absorb and re-emit radiation becomes a galactic-scale control mechanism. The gas within these clouds is primarily hydrogen, which is notoriously inefficient at radiating away its own heat. It needs a helper. That helper is dust. The dust grains, mixed thoroughly within the gas, act as incredibly efficient radiators. They absorb the thermal energy from the gas molecules and then re-radiate that energy away as infrared light, which escapes easily into space. This process acts like a cosmic air conditioner, systematically cooling the cloud from the inside out. As the temperature plummets, so does the gas pressure, allowing gravity to gain the upper hand and initiate the collapse into new stars. In this scenario, dust is the ultimate enabler of star birth, its cooling effect creating the precise conditions necessary for gravity to work its magic. But the story doesn't end there, because dust's regulatory role has a fascinating flip side. In other environments, particularly near newly formed massive stars or active galactic nuclei, the radiation field is so intensely powerful that the same dust grains can have the opposite effect. Instead of just calmly radiating energy away, they are bombarded by such a torrent of ultraviolet light that they heat up dramatically. This superheats the surrounding gas, causing it to expand violently and increase its pressure. In these regions, dust-induced heating becomes a powerful force that suppresses further star formation. It pushes back against gravity, preventing additional gas from collapsing and effectively putting a cap on how many stars can form in that particular neighborhood. It's a brilliant feedback loop. The first generation of stars produces intense radiation, which heats the dust, which then shuts down the formation of the next generation right next door. This dual nature, both promoter and suppressor of star formation, is what makes dust such a perfect cosmic thermostat. It doesn't just push the gas in one direction. It responds to local conditions, fine-tuning the star formation rate to maintain a kind of galactic equilibrium. We see dramatic evidence of what happens when this regulatory system is broken when we look at certain dwarf galaxies. These smaller galaxies often have very low metal content, which means they also have very little dust. Without this fine-tuning mechanism, their star formation becomes chaotic and erratic. They might experience a single, brief, and furious burst of star formation that consumes nearly all of their available gas at once, leaving the galaxy unable to form new stars for eons afterward. They lack the balancing feedback that dust provides, and their evolutionary path is fundamentally different and often shorter. As a result, this overarching regulatory function ensures that large galaxies don't burn through their fuel too quickly. It promotes a sustainable billion-year lifestyle, where star formation is a steady, ongoing process rather than a brief, brilliant flash in the pan. The dust, in its quiet, pervasive way, manages the galactic energy budget, cooling gas where it's too warm to collapse and heating it where it's getting too dense. It's the reason a galaxy like our Milky Way has been forming stars at a relatively steady rate for over 10 billion years, with enough gas left in the tank to continue for billions more. This isn't a chaotic universe, it's a managed one, and the unassuming dust grain is one of its most skilled and essential managers. But the life of a star is not an endless story. For all but the smallest stars, it culminates in a final, dramatic act of cosmic recycling. and this is where the true purpose of that internal alchemy is fulfilled. When a star dies, it does not go quietly. It returns its enriched substance back to the galaxy, and it does so by packing those newly forged heavy elements into solid, durable packages, grains of cosmic dust. This is the universe's ultimate recycling program, a cycle of death and rebirth on a galactic scale that ensures the cosmos grows richer and more complex with each passing generation. Consider the two primary ways a star can end its life. For the most massive stars, the finale is a supernova, a cataclysmic explosion of unimaginable power that tears the star apart from the inside out. In the furious heart of that blast, temperatures and pressures are so extreme that they act as a forge, creating elements even heavier than iron, like gold, silver, and uranium in a matter of seconds. This newly synthesized material, along with all the other elements the star created during its life, is then violently ejected into the surrounding space. But it doesn't just spray out as a cloud of isolated atoms. Incredibly, within the rapidly expanding and cooling cloud of debris, atoms quickly condense and stick together, forming trillions of microscopic dust grains, each one a tiny capsule carrying its precious cargo of heavy elements. For intermediate mass stars like our Sun, the end is more gentle but no less beautiful. In its final stages, a Sun-like star will swell into a red giant, pulsating and shedding its outer layers into space over thousands of years. This creates a magnificent, glowing shell of gas known as a planetary nebula. Within this slowly expanding cloud of stellar material, conditions are perfect for dust formation. As the gas cools, atoms of carbon, oxygen, and other elements condense out, forming soot-like carbon grains and crystalline silicate particles. These newly formed dust grains are then pushed outward by the pressure of the dying star's radiation, eventually becoming part of the interstellar medium. Whether through violent explosion or gentle expulsion, the result is the same. The galaxy is seeded with dust that is chemically rich, a direct product of stellar nucleosynthesis. This process of enrichment is not a one-time event. It's a continuous cycle that has been running for over 13 billion years. The very first stars in the universe, known as population 3 stars, were composed only of the primordial hydrogen and helium from the Big Bang. When they died, they were the first to create and distribute the heavier elements, enriching the pristine gas from which the next generation of stars would form. Those second-generation stars then built upon that initial enrichment, creating even more heavy elements in their cores and sending them out into the world when their time came. Our own Sun is a product of this long chain of stellar life and death. It is a third-generation star, its composition, and the composition of our entire solar system enriched by the dust from countless stellar ancestors. The evidence for this is written across the sky. When we look at the beautiful, intricate filaments of a supernova remnant like the Crab Nebula, or the delicate, glowing shells of a planetary nebula like the Helix Nebula, we are not just looking at a pretty picture. We are looking at a galactic delivery service in action. Spectrographic analysis of these objects confirms they are brimming with complex molecules and dust grains rich in silicon, carbon, and iron. This dusty debris doesn't just linger in empty space. It slowly mixes with other interstellar clouds. When that enriched cloud eventually collapses under gravity to form a new generation of stars and planets, it does so with a much richer chemical palette. This is why later generations of stars have higher metallicity, a higher proportion of elements heavier than hydrogen and helium. It's also the reason rocky planets like Earth can exist at all. The very iron in our blood, the calcium in our bones, and the silicon in the ground beneath our feet were all forged in the heart of a long-dead star, and delivered to the primordial solar system as part of a dust grain. This is the profound truth behind the words of astronomers like Dr. Sarah Johnson, who see dust as the universe's ultimate recycler. Without this mechanism, all those heavy, complex elements would remain forever locked inside the white dwarfs and neutron stars that are the corpses of dead stars. The interstellar medium would remain forever pristine and simple, only hydrogen and helium. New stars would form, but they would be barren and simple, utterly incapable of forming the complex structures of planets, much less the chemistry of life. The cosmic diversity we see today, the vast array of stellar types, the breathtaking variety of exoplanets, the potential for biology, all of it hinges on this continuous process of dust-enriched recycling. It turns the ashes of dead stars into the building blocks for new beginnings, ensuring that the galaxy is not a static museum but a dynamic, evolving, and ever-enriching ecosystem. So if you were to somehow remove all the stars and galaxies from the universe, would the cosmos be left in perfect, absolute darkness? It's a fascinating thought, but the answer is a resounding no. The space between the galaxies is not a void. It is filled with a faint, pervasive, universal glow. It's a background light that permeates all of creation, a whisper of energy that comes from no single source, but from everywhere at once. This is the cosmic infrared background, and it is a phenomenon that exists almost entirely because of the universe's countless trillions of dust grains, all tirelessly working to convert one form of light into another. This incredible process begins with starlight itself. Across the cosmos, stars of all sizes are pouring out immense amounts of visible and ultraviolet light. But as that light travels outward, a significant portion of it doesn't get very far before it is intercepted. It slams into the microscopic dust grains that are scattered throughout interstellar and even intergalactic space. These grains don't simply reflect the light like tiny mirrors. Instead, they absorb it. They take in that high-energy, short-wavelength radiation, and it causes them to physically vibrate, to heat up. Then, in accordance with the basic laws of physics, they must re-radiate that energy to cool down, but they don't re-emit it as the same visible light they absorbed. They release it as lower energy, longer wavelength infrared radiation, essentially as heat. It's a universal game of energy conversion, happening on a scale so vast it's almost impossible to comprehend. Every single dust grain, from the heart of a galaxy to the emptiest void, is acting like a tiny, inefficient light bulb, absorbing the brilliant visible light of the stars and glowing back with a warm, infrared hum. The collective effect of all these microscopic conversions is what creates the cosmic infrared background. It is the sum total of the heat from every dust grain in the observable universe, a diffuse fog of infrared light that fills the space between galaxies. For a long time, this was just a theoretical prediction. Detecting it was a monumental challenge because it is so incredibly faint, and because our own solar system is filled with zodiacal dust that creates a local infrared haze obscuring our view of the cosmic signal. It took dedicated space-based observatories, freed from the interference of Earth's atmosphere, to finally make this discovery. The C-Osmic Background Explorer, or COBE satellite, was the first to make a definitive detection of this infrared background in the 1990s. It revealed that the entire sky does indeed glow with this faint, ancient light. Later missions, most notably the Spitzer Space Telescope, were able to map this background in even greater detail, peeling back the layers of this universal veil. And what they found hidden within that faint glow was nothing short of revolutionary. This infrared background isn't just a uniform fog, it has structure and variation. By carefully analyzing its patterns, astronomers realized they weren't just looking at a simple energy field. They were looking at a hidden census of cosmic activity. A vast number of galaxies, particularly in the early universe, are so shrouded in dust that their visible light is completely obscured. They are invisible to optical telescopes like Hubble. But their dust is still there, diligently absorbing the intense light from furious bursts of hidden star formation and active black holes, and re-radiating it as infrared. The cosmic infrared background is in essence the aggregated light of all these hidden galaxies. It is the collective glow of universes we could not otherwise see. This allows astronomers to literally take a census of star formation across the entire history of the cosmos. They can measure how many stars were forming in these dust-obscured galaxies at different epochs, providing a much more complete and accurate picture of how galaxies assembled and evolved over billions of years. This transforms our understanding of cosmic history. For a long time, we had a biased view of the universe based largely on what we could see in visible light. We thought we were seeing most of the action, but the infrared background revealed that a huge amount of cosmic evolution was happening behind the scenes, hidden in dusty envelopes. Some of the most energetic and important phases of a galaxy's life, its most intense periods of star birth, are often completely shrouded in dust. Without this universal converter, this ability of dust to take the hidden light of the universe and convert it into an infrared signal we can detect, we would be completely blind to these dramatic chapters. The cosmic infrared background is therefore far more than just a curious energy field. It is a fundamental window into the true, hidden workings of the cosmos. It is the universe's way of ensuring that even its deepest secrets, veiled in dust, eventually find a way to shine through. When we step back and admire the grand tapestry of the universe, the majestic forms of galaxies are what first capture our imagination. We see elegant spirals with their sweeping arms, stately ellipticals glowing with ancient starlight, and bizarre, distorted galaxies locked in gravitational dances. For centuries, astronomers have classified these celestial islands based on their shapes, creating a taxonomy of the cosmos. But what if I told you that a significant part of what we're seeing, the very appearance and structure of these galaxies, is not just shaped by stars and gravity, but is dramatically influenced by the silent, pervasive presence of cosmic dust? It acts as both a sculptor and an artist, carving out details and painting shadows that define a galaxy's very identity. This influence is most breathtakingly obvious in spiral galaxies like our own Milky Way. When we look at a classic spiral galaxy edge-on, we don't just see a simple, flat disk of stars. Cutting directly through its center is a dark, thick, and dramatic band, a dust lane. This isn't an empty void. It's an incredibly dense concentration of interstellar dust and gas, so thick that it completely blocks the brilliant light from the billions of stars behind it. This dust lane isn't a flaw or an obstruction. It is a fundamental architectural feature. It defines the galaxy's thin plane and emphasizes its three-dimensional structure. The most iconic example of this is the magnificent Sombrero Galaxy. What makes the sombrero so instantly recognizable and gives it its name isn't just its bright central bulge of stars. It's the perfectly defined, razor-sharp dark lane that slices across it. That dark band is a colossal ring of dust, and without it, the sombrero would simply look like a fuzzy, egg-shaped glow. The dust provides the contrast, the shadow, the defining feature that makes it a celestial icon. It's a stunning reminder that what is absent, the blocked starlight, can be just as important to a galaxy's profile as the light that shines through. But dust's role in galactic morphology goes far beyond simply adding aesthetic details. it actively highlights the most dynamic and violent processes happening within a galaxy. When two galaxies collide a slow, billion-year-long gravitational tango, their structures are torn apart and remade. These interactions trigger massive waves of new star formation, and where there is star birth, there is dust. The furious energy of these newborn stars heats the surrounding dust clouds, causing them to glow intensely in infrared light. To an optical telescope, a merging galaxy might just look like a messy, irregular blob. But to an infrared eye, the dust reveals the true story. It outlines the tidal tails, the long, streaming arcs of stars and gas pulled out by gravitational forces. It illuminates the dense, dusty knots where new star clusters are igniting. The dust doesn't just participate in the merger, it acts as a highlighter pen, tracing out the forces of the interaction and marking the sites of the most intense cosmic action. By absorbing visible light and re-radiating it as infrared, the dust gives us a completely different and often more informative view of a galaxy's structure and history. This profound influence even extends to how we fundamentally classify galaxies. The famous Hubble tuning fork diagram, which places galaxies into neat categories of spirals, ellipticals, and irregulars, is based primarily on what we see in visible light. But we now know that a galaxy's appearance in visible light is only part of the story. A galaxy that looks like a quiet, red, and dead elliptical in optical images might be revealed as a dust-obscured monster in infrared, hiding a ferocious amount of star formation or a hidden active nucleus at its core. This means that dust doesn't just create the shapes we see, it can also deceive us, masking a galaxy's true nature and evolutionary stage. Our entire system of cosmic classification has had to evolve alongside our understanding of dust, forcing us to look at galaxies in multiple wavelengths of light to get the complete picture. The dust isn't just a component of the galaxy, it is an active designer, its distribution and density influencing gravitational collapse, the pressure within molecular clouds, and the overall balance of the interstellar medium. It helps determine whether a galaxy will maintain elegant, thin spiral arms or devolve into a more chaotic, irregular structure. From the grandest design to the smallest detail, cosmic dust is there, working in the background, ensuring that the galactic landscape is as rich, complex, and beautiful as it is. Up in the serene, silent darkness of a dense molecular cloud, a single, massive core of gas begins its inevitable collapse, pulled inward by its own immense gravity. It seems destined to become one giant, solitary star, but the universe has a flair for companionship, and often this singular fate is interrupted. The core doesn't just collapse, it breaks apart, fragmenting into 2, 3, or even more individual entities that will go on to spend their lives locked in a graceful gravitational dance. This beautiful act of cosmic multiplication, the birth of binary and multiple star systems, is a process that relies on a delicate and precise set of conditions. And once again, we find that the presence of cosmic dust is the critical ingredient that tips the scales, transforming what could have been a lonely stellar existence into a stellar partnership. The key to this fragmentation lies in the intricate physics of the collapsing core. As the giant ball of gas contracts, it doesn't just get denser, it also begins to spin faster, a consequence of conserving angular momentum, much like an ice skater pulling their arms in to spin more rapidly. This rotation creates a centrifugal force that fights against the inward pull of gravity, trying to flatten the core into a disk. At the same time, the core is heating up due to the compression, and this thermal pressure also pushes back against the collapse. For a single star to form, these forces need to be overcome. But for a binary system to be born, something else must happen. a gravitational instability must develop within the core, causing it to become lopsided and split into separate clumps that can then collapse independently. This is where cosmic dust performs its subtle magic. The dust grains mixed throughout the gas act as incredibly efficient radiators, siphoning off the thermal energy from the gas and re-radiating it away as infrared light. This cooling effect is the crucial catalyst. By lowering the internal temperature and pressure of the collapsing core, the dust weakens the force that was resisting fragmentation. It allows the core to become more susceptible to the tiny, initial asymmetries and ripples within it. A region that is just slightly denser than its surroundings can now more easily draw material to itself, growing at the expense of other areas, ultimately leading to a clean break. The dust-cooled core doesn't just collapse monolithically, it splinters like a breaking jewel under the strain of its own rotation and gravity. We don't have to look far to find stunning evidence for this theory. Nestled within the Great Orion Molecular Cloud Complex is a region astronomers have nicknamed the Binary Star Nursery. It's a dense, dusty pocket of space where telescopes like the Atacama Large Millimeter Array, or ALMA, have been able to peer deep into the hearts of these collapsing cores. What they've found is a veritable treasure trove of budding stellar systems. ALMA images don't show visible light, they reveal the faint radio waves emitted by the dust and gas itself. And in these images, we see not just single, glowing knots of material, but clear, distinct multiple sources within a single core. We see 2, and sometimes 3, bright condensations of dust, each one a nascent protostar, already separated and beginning to accumulate their own individual disks of material, all while orbiting a common center of gravity. These are binary and multiple star systems in the very earliest stages of their formation, caught in the act of being born from a fractured, dusty womb. It's direct observational proof that the processes we theorize are not just mathematical abstractions. They are happening right now, all across our galaxy. This role of dust in fostering stellar multiplicity is far more than a curious footnote. It has profound and cascading consequences throughout galactic evolution. The presence of a binary companion dramatically alters the environment for any potential planets that might form within the system. Planetary orbits can become unstable, leading to worlds being ejected into the cold depths of interstellar space or sent on wildly elliptical paths. Alternatively, the gravitational influence of 2 stars can shepherd material into stable zones, like the Lagrange points, potentially allowing planets to form and persist in places that would be impossible around a single star. Furthermore, binary systems are key players in some of the most energetic events in the cosmos. When one star in a binary pair evolves into a white dwarf, it can siphon material from its companion until it reaches a critical mass and explodes as a Type Ia supernova, a brilliant standard candle that astronomers use to measure vast cosmic distances. The rate of these supernovae, and therefore our ability to map the expansion of the universe itself, is directly tied to the population of binary stars. By enabling the formation of these stellar pairs, cosmic dust isn't just creating twins, it's indirectly calibrating our cosmic yardsticks and seeding the galaxy with the exotic events that disperse heavy elements and regulate its chemical evolution. In this way, the humble dust grain acts as a grand diversifier, ensuring that the stellar population of a galaxy is not a monotonous collection of single suns, but a rich and complex tapestry of singles, pairs, and intricate gravitational families, each with its own unique story and its own unique impact on the cosmic landscape. We've seen cosmic dust as a builder of stars, a guardian of planets, and even a trigger for galactic winds. But to truly appreciate its profound influence, we need to zoom out to the grandest scale of all, the complete life story of a galaxy itself. From its fiery birth in the early universe to its eventual quiet fade into old age, cosmic dust is there at every single step, not just as a bystander, but as an active participant that helps write every chapter of this billion-year saga. It is the golden thread that weaves through the entire cosmic tapestry, connecting the fate of individual stars to the destiny of the entire galactic system they call home. This incredible journey begins, of course, with creation. In the primordial clouds that collapsed to form the first galaxies, even the earliest generations of stars relied on the basic physics of dust to cool the gas and initiate their birth. As those first stars lived and died, they seeded their infant galaxy with the first heavy elements, which quickly condensed into the very first grains of cosmic dust. This was the moment the galaxy's life cycle became self-sustaining. With this initial dust enrichment, the next generation of star formation became more efficient, and soon planets began to form around those new stars. The dust was there, facilitating the collapse, protecting the protoplanetary disks, and enriching the interstellar medium with the complex molecules that are the precursors to life. In a galaxy's vibrant youth, dust is the engine of its growth and complexity, the substance that allows it to build itself up from a simple cloud of gas into a dazzling, structured island of stars and worlds. But as a galaxy matures, the role of dust begins to evolve, and it takes on a more complex, almost paradoxical dual nature. It can become an agent of both intense renewal and gradual demise. In the crowded central regions of an aging galaxy, vast amounts of dust can accumulate over time, funneled inward by gravitational forces and galactic dynamics. This central dust reservoir becomes a stockpile of fuel. Under the right conditions, this dust-rich gas can ignite a ferocious burst of new star formation. A starburst event that for a brief, brilliant period can make the galactic core shine with the light of millions of newborn stars. But this same stockpile of fuel also sits right at the doorstep of the galaxy's supermassive black hole. As the dust and gas swirl closer to the event horizon, they can feed the black hole, awakening it from its slumber and turning it into an active galactic nucleus. The incredible energy unleashed by this feeding black hole then drives powerful outflows and floods the galaxy with radiation. This feedback process, ironically fueled by the dust itself, can heat up or even blow away the remaining star-forming gas in the galaxy. It's a cosmic case of the galaxy literally burning its own fuel supply to shut down its future. This process, known as quenching, effectively ends the galaxy's ability to form new stars, dooming it to a long, slow fade as its existing stars age and cool. The very substance that enabled its vibrant life now contributes to its transition into old age. This overarching involvement makes dust far more than just a component. It is the physical embodiment of the cosmic cycle of creation and destruction. It is the universe's great recycler, carrying the ashes of dead stars into the cradles of new ones. It is the regulator, fine-tuning the rate of stellar birth to ensure a galaxy doesn't live too fast or die too young. And it is the connector, physically linking the life and death of individual stars to the grand evolutionary trajectory of their entire host galaxy. The dust forged in a supernova explosion 10 billion years ago might have helped form a planet around a distant star, and that same dust, or its descendants, might now be contributing to the quenching of a giant elliptical galaxy. Every tiny grain is a courier carrying both the materials and the energy that shape cosmic evolution. Reflecting on this, we see that a galaxy is not a collection of isolated events. It is a single, interconnected ecosystem, and cosmic dust is the medium through which every part of that system communicates, a constant reminder that in the cosmos, every ending truly is just a new beginning in disguise. Now, let's extend our gaze beyond the familiar confines of our cosmic neighborhood and peer across truly unimaginable distances to the very edge of the observable universe. Out there, billions of light-years away, lie the earliest galaxies, the first grand structures to coalesce after the Big Bang. For decades, these primordial islands remained among the most sought-after and elusive prizes in all of astronomy. Their light is so ancient that the expansion of the universe itself has stretched it, shifting it from the visible spectrum all the way into the infrared. This presented a seemingly insurmountable problem for traditional telescopes, which were designed to see the universe in visible light. But in a beautiful twist of cosmic irony, the very substance that often obscures our view in the nearby universe becomes our most powerful ally in the far reaches of space. Cosmic dust, by its very nature, transforms into a brilliant beacon, illuminating the earliest chapters of cosmic history. This incredible detective story hinges on a fundamental property of light and dust. When the universe was young, these first galaxies were often tumultuous places, undergoing ferocious bursts of star formation. All those brilliant, massive young stars poured out immense amounts of ultraviolet and visible light. But these galaxies were also incredibly dusty. The same violent stellar births and deaths that filled them with stars also quickly seeded them with heavy elements that condensed into vast clouds of dust. This dust did what it always does. It absorbed that energetic starlight. But rather than hiding these galaxies completely, this process actually made them more visible to the right kind of telescope. The dust, heated by the starlight, would re-radiate all that absorbed energy as a strong, warm glow in the infrared part of the spectrum. So, while the original visible light of the stars was being obscured and redshifted into near invisibility, the dust was busy converting that lost energy into a bright infrared signature that could travel across billions of light years. Without this dusty conversion process, these infant galaxies would be virtually undetectable. Their redshifted starlight would be far too faint for any telescope to pick up. It is the dust's emission, this secondary glow, that acts as a powerful signal flare announcing the presence of a hidden galaxy. This is where a telescope like the James Webb Space Telescope becomes an absolute game changer. JWST is not an optical telescope like Hubble. It is a premier infrared observatory specifically designed to see the heat signatures of the cosmos. It is the perfect instrument to detect the warm infrared glow of dust in the earliest galaxies. When JWST points its golden mirror at a patch of sky that appears empty to Hubble, it doesn't see nothing. It sees a field teeming with faint red smudges. Each one of those smudges is a distant galaxy. Its light has been traveling for over 13 billion years to reach us, and we are seeing it not by the light of its stars, but by the infrared glow of its dust. The dust is quite literally illuminating a path back in time, allowing us to conduct a census of galaxy formation during the cosmic dawn. This transformative capability is rewriting our textbooks on the early universe. For a long time, we theorized that the first billion years after the Big Bang were a relatively quiet period, a slow and gradual awakening of galactic structures. But the data from JWST, powered by its ability to see these dusty beacons, is revealing a startlingly different picture. It appears the early universe was a far more dynamic and intense place than we ever imagined, with massive, dusty galaxies and supermassive black holes forming at a breakneck pace much earlier than our models predicted. Every one of these distant, dusty galaxies is a data point, a clue that helps us map the timeline of cosmic evolution. By counting them, measuring their brightness, and studying their spectra, we can begin to understand how the first galaxies assembled themselves, how quickly they enriched themselves with heavy elements, and how they laid the groundwork for the universe we see around us today. In this profound and essential role, cosmic dust is far more than just a building block or a veil. It is a master historian, holding the light of the first galaxies within its grains and faithfully transmitting their stories across the eons for us to finally decode. But the journey of cosmic dust doesn't end with the grand architecture of a galaxy. Its most profound role might be the most intimate one of all, the silent cultivation of worlds where life itself can take root. This incredible connection bridges the vast emptiness of interstellar space to the specific, delicate conditions on the surface of a planet, suggesting that the very ingredients for biology are sown across star systems by the most unassuming of cosmic gardeners. To understand how this works, we need to follow the path of a single dust grain enriched with complex molecules. Imagine one of these microscopic specks, perhaps coated in a mantle of water ice and laced with organic compounds, drifting for eons within a cold molecular cloud. When that cloud finally collapses to form a new star, this grain becomes part of the swirling protoplanetary disk. It's too small to become a planet itself, but it doesn't need to be. Instead, it acts as a building block for much larger objects. Through countless collisions and gentle sticking, this grain and trillions of its siblings aggregate into ever larger bodies, first pebbles, then rocks, and eventually planetesimals, the mountain-sized precursors to planets. Some of these planetesimals will go on to form the rocky cores of worlds like Earth, but others, particularly those that form in the colder, outer regions of the disk, will become the comets and asteroids. These icy bodies are essentially frozen reservoirs, preserving within them the pristine water ice and probiotic chemistry that was originally carried on the surfaces of those ancient dust grains. They are the cosmic delivery trucks, and their cargo is the potential for life. This isn't just a theoretical idea for our own solar system. It's a story written into the very composition of our world. When Earth first formed, it was a seething, molten ball of rock, far too hot to retain any water or delicate organic molecules on its surface. Any such volatiles present during its accretion would have been instantly boiled away into space. So where did our oceans come from? Where did the carbon, nitrogen, and other essential elements for life originate? The prevailing theory points directly to a later delivery service, a period called the Late Heavy Bombardment, occurring hundreds of millions of years after Earth's formation, when the gravitational dance of the giant planets destabilized the outer solar system, flinging countless comets and water-rich asteroids inward. These icy impactors rained down upon the early Earth, and with them, they delivered vast quantities of water and complex organic materials. Every time you look at the ocean, you are looking at water that was, in its original form, a frozen coating on a speck of interstellar dust billions of years ago. The dust provided the raw ingredients, and the dynamics of the solar system provided the delivery mechanism. This profound link suggests that a galaxy's potential for life is directly tied to its dust content. A galaxy rich in metals and dust is a galaxy that has undergone multiple cycles of stellar death and rebirth, enriching its interstellar medium with the heavy elements necessary to form not just planets, but the specific molecules that are the precursors to biology. It's a galaxy that can form water-rich comets and carbonaceous asteroids in abundance. Conversely, a dust-poor galaxy, perhaps one in the early universe or an irregular dwarf galaxy, might still form planets, but they would be barren, rocky worlds without the volatile-rich impactors to provide them with oceans or an atmosphere conducive to chemistry. The dust, therefore, acts as a broad-scale regulator of habitability across the entire galaxy. It doesn't guarantee life, That requires a countless number of other factors to align perfectly, but it does dramatically expand the number of worlds where the experiment of biology can even begin. It fills the galactic pantry with the essential ingredients, making it possible for a planet, nestled in the just right habitable zone around its star, to become a true living world. So when we ponder our place in the cosmos, we can trace our existence back not just to a star, but to the countless generations of stars that came before it, whose ashes formed the dust that carried the promise of water and life across the light years, patiently waiting for a world like ours to receive it. Imagine two majestic islands of stars, each containing hundreds of billions of suns, slowly drawn together by the inexorable pull of gravity. This is not a gentle meeting. It is a billion-year-long cosmic dance that ends in a violent, transformative embrace. And while the gravitational forces are the architects of this colossal event, it is the vast reservoirs of cosmic dust within each galaxy that become the active agents of change, turning a catastrophic collision into a spectacular engine of creation and renewal. As the galaxies first begin their approach, their delicate structures are the first to feel the strain. Long before the stars themselves ever collide, the distances between them are so vast that stellar impacts are incredibly rare. The extended clouds of gas and dust that fill the galactic disks feel the gravitational disturbance immediately. They are pulled and stretched by tidal forces, creating immense, sweeping arcs that can extend tens of thousands of light years into space, forming the beautiful but destructive-looking tidal tails we see in so many merging systems. But the real drama begins when these extended clouds, now set on collision courses by the galactic interaction, finally slam into one another. Unlike stars, which mostly pass through one another harmlessly, these clouds are a different story. When a giant molecular cloud from one galaxy plows into a similar cloud from the other, the result is not a gentle mixing. It is a colossal shock wave, a supersonic collision that sends a violent ripple of compression through the gas and dust. This sudden, extreme increase in density is the ultimate trigger. It forces the gas to collapse under its own weight at a ferocious rate, igniting a firestorm of star birth known as a starburst. In a relatively quiet galaxy like our Milky Way, a handful of new stars might form each year. In the heart of a galactic merger, that rate can explode into hundreds or even thousands of stars annually, a veritable frenzy of creation on a scale that is almost unimaginable. We have a stunning front-row seat to this process in a famous pair of colliding galaxies known as the antennae galaxies. Their name comes from the two long, flowing tidal tails of stars and dust that have been pulled out by the interaction, making them look like the antennae of some giant cosmic insect. But if you look toward the galaxy's overlapping centers, the view is even more dramatic. That region is a blazing cauldron of activity, glowing intensely not with the blue light of individual stars, but with the warm, pinkish-red glow of hydrogen gas excited by the ultraviolet radiation from countless newborn massive stars. And peppered throughout that glow are brilliant, compact knots of dust-shrouded star clusters, each one containing millions of young stars. This is the starburst in action, a direct and spectacular result of the dusty gas clouds from both galaxies colliding, compressing, and erupting into a stellar baby boom. But the influence of dust in these cosmic crashes doesn't stop at making new stars. All that gas and dust being violently funneled toward the center of the merger has another, even more dramatic destination, the supermassive black hole that lurks at the heart of most galaxies. As the galactic collision funnels a literal river of fuel toward these dormant monsters, they begin to feast. The infalling material forms a furious, glowing accretion disk around the black hole, unleashing a torrent of energy that can outshine the entire rest of the galaxy. This awakening of the active galactic nucleus then pours energy back into its surroundings, driving powerful winds and jets that can regulate the very star formation that the merger initially sparked. It's a complex feedback loop where dust is both the kindling for the fire and a component of the bellows that fans it. This violent yet creative process is fundamental to the story of galactic evolution. Without the presence of copious amounts of dust to absorb the shock energy and efficiently cool the compressed gas, these collisions would be far less dramatic affairs. The clouds would likely pass through each other with less resistance, resulting in a slower, more subdued merger. There would be no brilliant starbursts, no rapid feeding of the central black holes, and therefore fewer of the quenching events that shut down star formation and create the smooth, featureless elliptical galaxies we see in the universe today. The dusty interactions act as an amplifier, taking the gravitational energy of the collision and converting it efficiently into luminous, transformative events. They ensure that a galactic merger is not just a simple restructuring of stars, but a profound life-altering event that can change a galaxy's identity forever, turning two serene spiral galaxies into a single, blazing elliptical or an irregular galaxy rich with new stellar generations. In the grand tapestry of the cosmos, dust is the element that turns a catastrophic collision into a catalyst for renewal, ensuring that from the most violent encounters, new diversity and structure can emerge. Yet for all its power to obscure, cosmic dust also provides the key to its own undoing, offering astronomers a way to correct their vision and achieve a level of precision in measuring the cosmos that would otherwise be impossible. This critical work of calibration is fundamental to one of the most important quests in all of science, determining the true scale of the universe and the rate of its expansion. When we look at a distant star or galaxy, its apparent brightness is one of our primary clues to its distance. The basic principle is simple: a candle looks fainter the farther away it is. In astronomy, we use certain types of stars and stellar explosions as these standard candles, objects whose intrinsic brightness we believe we understand. By measuring how dim they appear from Earth, we can calculate how far away they must be. This simple, powerful idea is the foundation for building our cosmic distance ladder, the step-by-step method we use to measure the vast scales of the universe. But this entire elegant system relies on a critical assumption: that the light from our standard candle has traveled to us in a straight line, unchanged and unobstructed. Cosmic dust is the wild card that shatters this assumption, introducing a variable that, if unaccounted for, can lead us wildly astray. The danger lies in the fact that dust doesn't just make things look dimmer, it makes them look farther. Imagine a specific type of supernova known as a type Ia. These are among our most important standard candles because they all explode with nearly the same peak brightness. When we spot one in a distant galaxy, we measure its apparent brightness, plug it into our equations, and out pops a distance. But what if there's a patch of interstellar dust between us and that supernova that we didn't know about? The dust absorbs and scatters some of the supernova's light, making it appear dimmer than it truly is. Our calculations, unaware of this dusty veil, will incorrectly tell us that the supernova is much more distant than it actually is. A single unnoticed dust cloud can therefore insert a massive error into our measurement of the distance to that galaxy. Now scale that error up across the entire universe. Our maps of cosmic structure, our measurement of the Hubble constant which describes the rate of the universe's expansion, and even our inferences about the mysterious force of dark energy that is accelerating that expansion. All of these foundational pillars of modern cosmology rely on the accuracy of these distance measurements. An uncorrected dusty veil doesn't just blur our view, it systematically distorts our entire understanding of the scale, history, and ultimate fate of the cosmos. This is why the meticulous science of dust mapping has become so utterly essential. Astronomers have had to become cosmic cartographers of the invisible, creating detailed three-dimensional atlases of dust distribution throughout our galaxy and beyond. They do this by observing the same patch of sky across multiple wavelengths of light. They look at hundreds of thousands of stars, measuring not only their brightness but, crucially, their color. Because dust scatters blue light more effectively than red, it doesn't just dim a star, it reddens it. By comparing a star's observed color to its expected, intrinsic color, scientists can calculate exactly how much reddening it has undergone, and from that, they can deduce the amount of dust along our line of sight to that star. By repeating this process for stars at many different distances, they can build up a layered map showing not just if dust is present, but how much and where it is. This dusty topography is then overlaid onto all other observations. When a cosmologist measures the light from a distant supernova, they don't just take the number at face value. They first consult the dust map for that precise direction in the sky. They find the correction factor, and they mathematically subtract the effect of the dust, peeling back the veil to reveal the supernova's true brightness. Only then, with this cleaned and calibrated data, do they feel confident in calculating a distance. This refining role transforms dust from a mere nuisance into an indispensable partner in precision cosmology. It forces a rigor upon the field that has ultimately made our models infinitely more robust. The quest to measure dark energy, for instance, which relies on comparing the distances to supernova across vast cosmic time, would be hopelessly compromised without these detailed dust corrections. The ongoing tensions in measurements of the Hubble constant, where different methods seem to yield slightly different expansion rates, are being intensely scrutinized, with the potential role of undetected or imperfectly modeled dust being a major focus of investigation. In this way, dust acts as the ultimate quality control. It is the necessary complication that keeps scientists honest, constantly reminding them that the universe is a messy, complex place, and that achieving true understanding requires us to account for every variable, no matter how small or seemingly insignificant. The humble dust grain, therefore, does more than just shape galaxies. It actively sharpens the very tools we use to understand them, ensuring that our quest to measure the cosmos is grounded in ever greater clarity and precision. Now consider the life of a star not as a steady, unwavering beacon, but as a dynamic, breathing entity that can flicker, dim, and blaze with a rhythm all its own. This stellar variability is one of the key ways astronomers decode the inner workings of stars, and for a fascinating class of these variable stars, the entire dramatic performance is orchestrated by the formation and dissipation of cosmic dust right in their own atmospheres. This isn't dust from an external cloud passing by. This is dust born from the star itself, a product of its own late-life chemistry that then turns around and fundamentally alters the star's appearance and behavior. To witness this in action, we can look to the Mira variables, a class of pulsating red giant stars named after the first known example, Mira itself, the wonderful, in the constellation Cetus. These are aging, sun-like stars that have exhausted the hydrogen fuel in their cores and have swollen to enormous sizes, becoming unstable. They rhythmically expand and contract over periods of hundreds of days, and with each pulsation, their outer layers cool dramatically during the expansion phase. This cooling is the crucial trigger. It allows atoms of elements like carbon, silicon, and oxygen forged in the star's own core to meet and condense into tiny solid particles right there in the extended stellar atmosphere. In essence, the star is manufacturing its own clouds of soot and sand. These newly formed dust grains do not stay put. The intense radiation pressure from the star's hot interior acts like a constant wind, pushing these dust clouds outward, away from the surface. For a time, this expanding shell of dust can grow so thick that it shrouds the star entirely, causing its visible light to plummet dramatically. Then, as the shell continues to expand and dissipate into the surrounding space, the star gradually re-emerges, brightening until the next cycle begins. This periodic veiling and unveiling, driven by the star's own pulsation and dust production, creates a beautifully predictable light curve that has allowed astronomers to study these processes for centuries. But if mirror variables represent a gentle, rhythmic breathing, then the Coronary Borealis stars are the cosmic equivalent of a violent, unpredictable cough. These are incredibly rare, hydrogen-deficient supergiants, and their variability is anything but regular. They will spend most of their time shining at a steady maximum brightness. Then, without warning, they will suddenly and catastrophically dim, sometimes by a factor of hundreds over just a few weeks. They can remain faint for months or even years before abruptly snapping back to their original brilliance. The culprit, once again, is internally produced dust. The prevailing theory suggests that these stars periodically belch out a huge cloud of carbon-rich gas. As this cloud expands and cools away from the star's surface, a vast quantity of carbon dust condenses almost instantaneously, forming an opaque, black cloud that completely blocks our view of the star. The dimming isn't gradual, it's a cliff-edge drop in brightness. The star only reappears when this sooty cloud has either drifted far enough away to become more transparent or has been pushed away by the star's radiation pressure, effectively clearing its own atmosphere. This erratic behavior provides a starkly different window into mass loss, showing us how some stars can shed their material not in a steady stellar wind, but in violent, discrete eruptions. This intimate connection between dust and starlight is far more than just a celestial light show. It is a critical diagnostic tool. By carefully studying the timing, depth, and color changes during these dimming events, astronomers can deduce the chemical composition of the dust, the temperature at which it condenses, and the dynamics of the stellar wind carrying it away. This tells us what the star is made of and how it is shedding mass in its final stages. For a star like our Sun, this process of dust-driven mass loss will be its fate billions of years from now. The dust it creates will eventually form a vast planetary nebula, enriching the interstellar medium for future generations. Without the dramatic variability caused by dust, these late-stage stellar processes would be far more subtle and difficult to observe from vast distances. The dust provides the punctuation in the sentence of a star's life, creating clear, observable events that mark its transition into old age. It reminds us that a star's demise is not a quiet fading but an active, complex transformation, and the dust it produces is both a byproduct of that change and an active agent in shaping its final act. Yet for all the drama contained within a single galaxy, the story of cosmic dust does not end at the galactic frontier. Through the immense forces we've just witnessed, the powerful galactic winds and the violent chaos of mergers, dust is routinely cast out, catapulted beyond its home galaxy and into the vast, seemingly empty expanses between galaxies. This intergalactic space, often thought of as a true void, is in fact being subtly seeded and transformed by these tiny interstellar travelers, building a faint, invisible bridge that connects all galaxies into a single, interconnected ecosystem. This incredible journey begins with the most energetic events a galaxy can produce. When a supermassive black hole at a galaxy's core becomes active, it doesn't just light up. It can unleash jets of radiation and matter that punch far beyond the galactic disk. Similarly, the collective force of a starburst region, where thousands of supernova explode in quick succession, can drive a super wind that blows right through the galaxy's gravitational grasp. These aren't gentle breezes, they are hypersonic tsunamis of hot gas, and because cosmic dust is so thoroughly mixed with this gas, it gets caught up in the flow. The dust grains, though small, are carried along by this torrent of energized particles, riding the shockwaves out of the galaxy and into the great nothingness beyond. It's a one-way trip, an ejection from the galactic homeland into the coldest, most diffuse environment in the universe. Once liberated into the intergalactic medium, this dust performs two revolutionary roles. First, it acts as a courier of heavy elements. The dust grains themselves are literally made of metals elements like silicon, carbon, and iron forged in stellar cores. By transporting these grains into the void, galaxies are effectively fertilizing the barren spaces between them with the raw ingredients for planet and star formation. This means that when a pristine cloud of primordial gas, mostly hydrogen and helium from the Big Bang, begins to collapse to form a new galaxy in the distant future, it might not be so pristine after all. It could already be lightly enriched with these metals from a long-ago galactic wind, giving the next generation of stars and planets a head start on complexity. The second, even more fascinating role is that these dust grains can act as nucleation sites. In the deep cold of intergalactic space, a lone hydrogen atom might struggle to find a partner to bond with. But if it encounters a floating dust grain, it has a solid surface to latch onto. Over eons, these grains could become the seeds for new molecular clouds, even in the profound emptiness between galaxies, potentially kick-starting the process of structure formation in places where it might otherwise never begin. We can actually observe this process at work in immense galaxy clusters like the famous Virgo cluster. These clusters are not just collections of galaxies, they are also filled with a superheated plasma known as the intracluster medium. When astronomers point X-ray telescopes at this plasma, they see the brilliant glow of incredibly hot gas. But when they look with infrared and radio telescopes, they find something astonishing mixed within that seething heat, cold dust. This dust could not have formed in the hot plasma. It must have been blown out from the cluster's galaxies. Its presence there is direct evidence of this intergalactic dispersal, showing that the material from individual galaxies doesn't just stay put, it pollinates the entire cluster. This paints a picture of the cosmos that is far more connected than we ever imagined. As astrophysicist Dr. Ryan Chen observes, dust truly does bridge galaxies. It forges a physical link, a web of material exchange that operates on scales of millions of light years. This intergalactic journey ensures that no galaxy is an isolated island. They are all part of a vast, circulating system, constantly sharing the products of their internal evolution with the wider universe. The dust that might one day form a mountain on a planet in a distant galaxy could have begun its life ejected from a star that died billions of years ago in an entirely different galactic neighborhood. It's a cycle of exchange that ties the fate of galaxies together, making the large-scale structure of the universe not just a gravitational masterpiece, but a chemical and thermodynamic one as well, all orchestrated by the smallest of particles. Yet as we pull our gaze back to the very dawn of time itself, to the first fleeting moments after the Big Bang, we find cosmic dust playing perhaps its most profound and paradoxical role of all. It sits at the very heart of our quest to understand the origin of everything, acting as both a frustrating obstacle and an indispensable guide in our search for the holy grail of cosmology, the primordial fingerprints of cosmic inflation. This incredible story begins with the oldest light in the universe, the cosmic microwave background, or CMB. This is the faint, cold afterglow of the Big Bang, a snapshot of the universe when it was a mere 380,000 years old, finally cool enough for light to travel freely. Imprinted upon this light are tiny, minuscule fluctuations in temperature, hot and cold spots that represent the seeds of all future structure, the gravitational blueprints for everything from galaxies to galaxy clusters. But hidden within this ancient light is an even more precious signal, one that physicists have been chasing for decades, a specific pattern of polarization known as B modes. These are a faint swirling pattern in the direction of the light's vibration, and they are theorized to be the direct signature of gravitational waves rippling through the fabric of space-time during a period of hyper-expansion called inflation, a trillionth of a second after the universe began. Detecting these primordial B modes would be like finding the first fossil, providing our first direct evidence for what happened at the very birth of the cosmos. But there's a monumental problem. The universe is filled with a polarizing filter of its own, cosmic dust. The same elongated dust grains that align with galactic magnetic fields don't just affect starlight. They also polarize the CMB radiation as it passes through them on its 14 billion-year journey to our telescopes. This interstellar dust creates its own B-mode polarization pattern, a foreground signal that is often orders of magnitude stronger than the faint inflationary whisper cosmologists are trying to hear. For a time, this presented a seemingly insurmountable barrier. The dust signal wasn't just noise, it was a brilliant, confounding mimic, a false positive that could easily be mistaken for the real thing. An initial, exciting detection of B modes by the BICEP 2 telescope in 2014 famously turned out to be, upon closer scrutiny with data from the Planck satellite, almost entirely attributable to this polarized dust emission from within our own galaxy. It was a sobering lesson in humility, demonstrating that to hear the faint echo of creation, we must first learn to listen through the constant rustle of the dusty present. This is where dust's role flips from contaminant to calibrator. Rather than giving up, cosmologists realized that to find the truth, they first had to understand the liar. This launched a monumental effort to map the polarization of galactic dust with unprecedented precision. The European Space Agency's Planck mission was pivotal in this endeavor. While its primary goal was to map the CMB, it also produced the most detailed all-sky map of this polarized dust emission ever created. It revealed an intricate, filamentary web of dust polarization across the entire sky, a beautiful but complicating tapestry that had to be meticulously characterized. This dusty map didn't ruin cosmology, it saved it. It provided the essential reference guide, the dusty foreground template that all subsequent experiments could use. Now, when a telescope like the BICEP array or the South Pole telescope points at a seemingly clean patch of sky to search for primordial B modes, it doesn't just look at its own data. It cross-references its findings with the Planck dust map for that exact line of sight. By carefully measuring the properties of the local dust, its intensity, its spectrum, its polarization angle, scientists can mathematically model and subtract its contaminating signal from their data. It's a painstaking process of peeling away the layers of the cosmic onion, with the dust map acting as the guide to removing the outermost skin. This dual identity makes cosmic dust a crucial partner in the most fundamental investigation of all. Its pervasive presence forces a rigor and a precision upon the field that has ultimately made the search for inflation far more robust. It ensures that any future claim of a detection will be ironclad, having passed the most stringent tests to rule out this galactic imposter. The dust, therefore, does more than just obscure, it validates. It is the control experiment written across the sky, the necessary complication that guarantees that when we finally do hear the true whisper of the Big Bang, we can be absolutely certain of what we're hearing. In this ultimate quest, the smallest particles in the universe have become the guardians of its biggest secret, ensuring that our story of origin is not built on sand, but on a foundation of dust, meticulously understood and accounted for. But while grand spirals and colliding giants capture our attention with their dramatic tales of dust-enriched evolution, some of the most profound lessons are written in the faint, quiet scripts of the universe's smallest galaxies. Dwarf galaxies, these modest collections of a few billion stars or less, live a completely different cosmic life than their majestic cousins, and a primary reason for their unique destiny boils down to a simple yet critical deficiency: a life of dust poverty. Imagine a fledgling dwarf galaxy in the early universe. It forms from a cloud of gas, but because it has a lower total mass, its gravitational pull is weaker. It cannot easily retain the heavy elements blasted out by its first generation of supernova. That enriched material often escapes its tenuous grasp, blowing out into intergalactic space. This means that subsequent generations of stars form from gas that is still relatively pristine, poor in the metals that are the essential building blocks of cosmic dust. Without this crucial ingredient, the entire cycle of star formation is thrown into disarray. In a massive galaxy, dust provides the efficient cooling that allows large, dense molecular clouds to fracture and collapse into stars. In a dust-poor dwarf, that regulatory system is broken. The gas has a much harder time shedding its thermal energy. It stays warmer, its internal pressure remains higher, and it fiercely resists the gravitational collapse that would birth new stars. This doesn't stop star formation entirely, but it makes it wildly inefficient and unpredictable. Instead of the steady, sustained star formation seen in spirals, dwarf galaxies often experience brief, violent, and isolated starbursts. They might go for hundreds of millions of years in relative quiet, then suddenly ignite in a furious but short-lived burst of activity that consumes a significant chunk of their remaining gas in one go, only to fall silent again for eons. This erratic rhythm leaves them structurally unevolved, often retaining irregular, chaotic shapes instead of settling into the elegant disks or spheroids of larger galaxies. This dust-driven disparity in their internal mechanics has cascading effects that extend far beyond their visible stars. The rate and rhythm of star formation are intimately tied to how dark matter is distributed within a galaxy. The powerful outflows from supernova in those brief starburst phases can push against the surrounding dark matter halo, effectively smoothing it out and creating a flatter, more homogeneous distribution in the galactic center. In dust-rich galaxies where feedback is more regulated, the dark matter profile can remain more peaked. This means that by studying the faint, irregular forms of dwarf galaxies and measuring their star formation histories, astronomers can actually infer details about the nature and distribution of the invisible dark matter that makes up most of their mass. The dust content, or lack thereof, becomes an indirect probe into the most mysterious substance in the universe. We can see this story play out in our own cosmic backyard within the local group of galaxies. Consider the Large Magellanic Cloud, a dwarf galaxy orbiting our Milky Way. It is relatively massive for a dwarf and has managed to hold onto enough enriched material to possess a modest amount of dust. And tellingly, it shows clear signs of structured spiral features and has sustained star formation for much of its life. Now compare it to the smaller, fainter dwarf spheroidal galaxies like Leo I or Draco. These are ancient, quiescent, and almost completely devoid of dust and gas. Their star formation ended long ago, after that initial burst consumed their fuel without the means to efficiently recycle it. They are fossilized remnants of the early universe, their evolution stunted by their inability to retain the dusty ingredients necessary for continuous renewal. Their faint, irregular forms are a direct signature of their dust poverty. This understanding fundamentally changes how we view galactic diversity. For a long time, a galaxy's mass was thought to be the primary driver of its fate. But we now see that chemical composition, specifically the presence of dust, is an equally powerful modifier of evolutionary pathways. Two galaxies of similar initial mass can end up on wildly different trajectories based simply on their ability to generate and retain these tiny grains. Dust acts as the great galactic equalizer, a substance that empowers even smaller galaxies to complexify and sustain themselves, while its absence can leave them frozen in time. It ensures that the tapestry of the cosmos is woven with threads of immense variety, where size is not the sole author of destiny, but where the smallest of particles can dictate the grandest of outcomes. Deep within the turbulent hearts of stellar nurseries and swirling around the violent environments of newborn stars, nature creates its own versions of incredibly powerful lasers. But these aren't beams of visible light. They are masers' microwave amplification by stimulated emission of radiation. These natural phenomena generate intensely bright, focused beams of microwave light, and they act as some of the most precise beacons in the entire universe. But for these cosmic lasers to ignite, they require a very specific set of conditions: a dense cloud of the right kind of gas, a powerful energy source to pump it, and crucially, a surrounding environment rich in cosmic dust to make the entire process possible. The mechanics of a cosmic maser are both elegant and intricate. They often occur in regions where molecules like water, silicon monoxide, or hydroxyl are abundant. For a maser to fire up, these molecules need to be energized or pumped into an excited state. This is frequently achieved by the intense infrared radiation pouring out from a nearby protostar or a young, massive star. But that powerful infrared radiation itself has a specific origin. It's the light from that young star that has been absorbed by the surrounding cocoon of cosmic dust and re-emitted as heat. So the dust acts as the initial energy converter, taking the star's visible and ultraviolet light and transforming it into the infrared pump that energizes the molecular gas. Once pumped, the molecules are primed. Then, when a passing microwave photon of the exact right frequency triggers them, they release their stored energy in a chain reaction, all emitting in perfect phase and in the same direction. The result is not a diffuse glow, but a brilliant, coherent beam of microwave radiation that can be detected across staggering interstellar distances with radio telescopes here on Earth. This turns otherwise obscure and complex regions into pristine laboratories for measurement. Because a maser spot is so small and its emission is so narrowly focused, it acts like a perfectly defined point of light in the sky. Astronomers can use a technique called Very Long Baseline Interferometry, or VLBI, to combine signals from radio telescopes scattered across different continents, effectively creating a virtual telescope the size of the entire planet. This gives them an resolving power so immense they can not only pinpoint the location of a maser spot with incredible accuracy, but they can also track its subtle movements over time. For example, in a galaxy millions of light-years away, they can identify individual water masers orbiting the supermassive black hole at the galaxy's core. By meticulously mapping the positions and velocities of these masers over months and years, they can directly trace the Keplerian rotation of the accretion disk, allowing them to calculate the mass of the central black hole with unparalleled precision. This same technique is used closer to home to map the spiral arms of our own Milky Way. By measuring the parallax and proper motion of masers in distant star-forming regions, we can triangulate their distances and velocities, helping us build an accurate three-dimensional map of our galaxy's structure, something that is incredibly difficult to do from our embedded position within it. The connection to dust is absolutely fundamental to this entire process. Without the dense, dusty envelopes surrounding young stellar objects, the intense infrared pumping radiation would simply escape into space, never interacting with the molecular gas long enough to create the population inversion needed for maser action. The dust provides the confined, energized environment where these molecular amplifiers can thrive. We see this clearly in places like the Orion KL Nebula, one of the most active and studied star-forming regions in our galaxy, which is also a famous powerhouse for numerous different types of masers. Its brilliant microwave emissions are a direct consequence of its incredibly dense and dusty core, where new stars are violently shaking up the surrounding soup of gas and molecules. This amplifying role showcases how dust does more than just build or obscure. It can also illuminate in the most precise way imaginable. By enabling the formation of cosmic masers, dust creates incredibly bright and stable landmarks against the dark backdrop of space. It provides the tools for astronomers to perform ultra-precise astrometry, measuring distances across the galaxy, and beyond that would otherwise be fraught with uncertainty. These natural lasers transform chaotic stellar nurseries and the chaotic regions around black holes into clean, well-defined laboratories, allowing us to test the laws of physics and measure the masses of celestial monsters with an accuracy that was once thought impossible. In doing so, dust once again proves that its most significant impacts often come from setting the stage for nature's most extraordinary and useful phenomena. Imagine for a moment the entire multi-billion-year life of a galaxy, from its fiery birth to its quiet old age, compressed into a single day. The sequence of events in that day, when star formation peaks, when it slows, when the galaxy transforms its very identity, is not set in stone by gravity alone. It is orchestrated in large part by the silent, pervasive presence of cosmic dust, which acts as a master clock, regulating the tempo of this grand cosmic evolution and ensuring that no two galaxies ever experience the same exact day. To understand this, we need to look at the two most dramatic transformations a galaxy can undergo. The first is the transition from a blue, star-forming spiral, vibrant with young, hot stars, to a red, quiescent elliptical, dominated by older, cooler stars and largely devoid of the gas needed to make new ones. The second is the process of quenching, where the furious rate of star formation is abruptly shut off. The timing of these events is everything, and it is here that dust exerts its subtle yet powerful influence as a galactic pacemaker. In a dust-rich galaxy, the cycle of star formation is fine-tuned. The dust's cooling effect allows for efficient, sustained star birth, but its role in driving powerful feedback winds can also remove gas and suppress future formation. This creates a balanced, self-regulating system where the galaxy can maintain a steady pace of stellar production for billions of years, delaying its transition into old age. Conversely, in a dust-poor galaxy, this regulatory mechanism is broken. Star formation becomes erratic and inefficient, often leading to a single, brief, and furious starburst that consumes the available fuel in a cosmic blink of an eye, accelerating the galaxy's journey to a red and dead state. We are no longer merely theorizing about this process. We can now witness it unfolding inside powerful supercomputer simulations. When astrophysicists build virtual models of galaxies, they must account for a dizzying number of factors: gravity, gas hydrodynamics, radiation, magnetic fields, and the feedback from supernova and black holes. For a long time, the role of dust was often simplified or even left out entirely, because its microphysics are incredibly complex to simulate. But the latest and most sophisticated models are now incorporating dust as an active ingredient, and the results are transformative. These simulations show that when dust physics are included, the virtual galaxies behave differently. Their star formation histories become smoother and more extended. The powerful outflows driven by supernova are modulated by the dust's ability to absorb radiation and help drive winds. The entire evolutionary timeline of the galaxy shifts. A simulation that might have previously shown a galaxy quenching after 2 billion years might now show it continuing to form stars for 6 or 7 billion years, all because the dust provided a regulatory feedback that prevented it from burning out too quickly. These digital universes are telling us that if you ignore dust, you get the wrong answer for one of the most fundamental questions in astronomy: how long does a galaxy live? This has profound implications for the incredible diversity we see in the galactic population. Why do some galaxies look like our Milky Way, a graceful spiral still actively giving birth to new stars after over 10 billion years? And why do others look like Messier 87, a giant elliptical that concluded its star-forming eons ago? Their differing dust content is a key part of the answer. The amount of dust a galaxy possesses and its ability to retain that dust against powerful winds acts as a primary dial controlling its evolutionary speed. It adds a layer of rich variation to the cosmic narrative, ensuring that while gravity sets the stage, dust often directs the play, determining the pacing of each act and the timing of the final curtain. This makes the cosmos a far more interesting and varied place, a universe where galaxies are not just assigned a fate based on their mass, but where their own internal chemistry and physics help them write their own unique stories, each ticking to the rhythm of its own dusty clock. For decades, astronomers have been captivated by a tantalizing theoretical possibility: the existence of dark galaxies. These would be vast, massive structures, teeming with the primordial gas from the Big Bang, but with a puzzling and profound absence of the stars that normally define a galaxy. They would be cosmic ghosts, invisible to optical telescopes, floating through the universe as missing links in our understanding of how galaxies assemble. How do you find something that, by its very definition, gives off no light? The answer, it seems, might once again be written in the faint, warm glow of cosmic dust. The theory behind these dark galaxies is compelling. Our standard model of cosmology suggests that dark matter halos are the gravitational seeds around which all galaxies form. These halos pull in vast amounts of gas, which then cools, condenses, and eventually fragments to form stars. But what if, in some halos, that process gets stalled or prevented entirely? Perhaps the gas is too spread out, or maybe a nearby galactic event heats it up just enough to suppress star formation while leaving the gas cloud intact. The result would be a stable, long-lived reservoir of gas, a galaxy-sized cloud that never ignited. For a long time, these objects remained purely hypothetical, their potential existence a frustrating gap in our cosmic senses. We had no way to see them. Their neutral hydrogen gas might emit a faint radio signature, but that signal is incredibly weak and difficult to distinguish from the background noise of the universe. They were, for all intents and purposes, invisible. This is where the unique properties of cosmic dust offer a brilliant solution. Even if a dark galaxy has failed to form many or any stars, it doesn't necessarily mean it is completely pristine. It could have been lightly polluted by earlier events, For instance, a nearby supernova in a passing galaxy could have blasted heavy elements and dust into intergalactic space, some of which might have been captured by the dark galaxy's gravitational pull. Alternatively, the few stars that might have managed to form within it could have already lived and died, seeding their immediate surroundings with a first generation of dust before star formation shut down completely. This means that a dark galaxy, while devoid of the brilliant light of stars, could still contain a sparse population of dust grains, and as we know, dust is a brilliant converter of energy. Even the faint, ambient ultraviolet light that permeates the universe from all the other galaxies could be absorbed by these dust grains. They would heat up just a few degrees above absolute zero and re-emit that energy as a very specific, faint signature in the far infrared and submillimeter wavelengths. This dusty whisper is the key that astronomers are now using to try and unlock this mystery. Powerful, modern telescopes and interferometers like the Atacama Large Millimeter Array are specifically designed to detect this cold, faint emission. Observational campaigns are now actively scanning the skies, particularly around regions where the environment might be ripe for creating these failed galaxies, such as near the edges of large galaxy clusters or in cosmic voids. They are not looking for points of light. They are looking for faint, extended, and smooth glows of infrared radiation that cannot be explained by any known visible object. It's like trying to find a ghost by the faintest footprint it might leave in the cosmic sand. The potential discovery of a true dark galaxy would be a monumental breakthrough. It would validate a whole class of theories about alternative pathways in galactic evolution. It would show us that the universe can create structures that defy our standard definitions, forcing us to expand our understanding of what a galaxy even is. Furthermore, these dark galaxies could act as cosmic time capsules, preserving pockets of gas that have been less processed by stellar nucleosynthesis, giving us a clearer view of the raw materials that were available in the early universe. They represent the ultimate frontier of galactic diversity, and it is the faint, persistent glow of dust, the substance we once thought of as mere space dirt, that is now our most promising guide into this profound darkness, proving that even when the stars refuse to shine, the universe still finds a way to reveal its secrets. And so we arrive at the final, and perhaps most forward-looking, of these 28 unbelievable ways, the role of cosmic dust in shaping the very future of galactic exploration itself. We are standing on the brink of a new astronomical revolution, an era defined not by a single type of telescope, but by a symphony of different messengers. This is the age of multi-messenger astronomy, where we don't just see the cosmos. We listen to its gravitational waves, detect its ghostly neutrinos, and measure its magnetic fields, all to build a complete, multi-dimensional picture of the universe. And in this new, complex endeavor, the humble dust grain is poised to become one of our most critical and most challenging partners. Its pervasive presence means that to understand the signals from these new instruments, we must first become masters of the dusty veil that hangs between us and the sources we wish to study. Consider the incredible precision required to interpret the signals from gravitational wave observatories like LIGO and Virgo. These facilities detect the faint ripples in spacetime caused by cataclysmic events like the merging of black holes and neutron stars. To pinpoint the exact location of these events in the sky, astronomers rely on a technique called triangulation, often using traditional telescopes to find the optical or infrared counterpart of the merger. But if that light has to travel through an unmapped cloud of interstellar dust on its way to us, its signal will be dimmed and reddened. If we don't accurately account for that dust extinction, we could misjudge the true distance and energy of the event, throwing off our calculations of the masses involved and the nature of the explosion. The dust in this context isn't just a blur, it's a potential source of critical error in our most precise measurements of the universe's most violent phenomena. The same is true for neutrino detectors, which track these nearly massless particles from supernova and other cosmic engines. To fully understand the environment that created those neutrinos, we need to model the surrounding material that is often rich with dust. This necessity is driving a monumental shift in how we prepare for future discoveries. It is no longer sufficient to build a stunning new telescope like the Nancy Grace Roman Space Telescope or the extremely large telescope and simply point it at the sky. The data it returns will be filled with the subtle, corrupting fingerprints of dust. Therefore, a huge part of the scientific preparation for these missions is not just building the hardware, but building the software, sophisticated computer models that can simulate how dust of different compositions, sizes, and shapes interacts with light at every wavelength. These digital dust models are then integrated into the analysis pipelines for every major observatory. Before an astronomer can study the atmosphere of a distant exoplanet to search for signs of life, they must first run the observed starlight through a dust filter algorithm, subtracting out the effects of any intervening interstellar grains to reveal the planet's true spectral signature. Before a cosmologist can use a distant galaxy to test dark energy models, they must consult a three-dimensional dust map of the entire line of sight to correct the galaxy's observed brightness and color. Dust modeling has moved from a niche specialty to a foundational requirement for all of astronomy. This transforms our perspective entirely. We can no longer view cosmic dust as a simple obstacle to be overcome. Instead, we must embrace it as an indispensable guide. Its very interference forces a rigor and a depth of understanding upon us that we would otherwise lack. The quest to see through the dust has led to entirely new technologies and methodologies. It compels us to observe the universe in multiple wavelengths simultaneously, because the story told by the infrared light from the warm dust is just as important as the story told by the visible light from the stars. It pushes us to build more complex and realistic simulations of galaxy formation, because if a simulation does not include the physics of dust formation, destruction, and its interaction with radiation, it will never accurately reproduce the galaxies we see in the real universe. In this way, dust is actively shaping the next frontiers of discovery, dictating the questions we must answer and the tools we must build to answer them. So as we prepare to peer into the atmospheres of distant worlds with the next generation of telescopes, or to listen for the echoes of the Big Bang with future cosmic microwave background missions, we carry with us a profound and humbling lesson from our journey through these 28 ways. The biggest secrets of the cosmos, the nature of dark energy, the origin of life, the fate of galaxies, are not always hidden in the grandest, most massive objects. Often they are encoded in the physics of the smallest particles, the silent, countless specks of dust that drift between the stars. They are the universe's constant reminder that to understand the infinite, we must first master the infinitesimal. From the majestic birth of stars in dusty nurseries to the violent, transformative clashes of entire galaxies, our journey through these 28 incredible roles reveals a universe orchestrated by the most unassuming of maestros. We've seen how cosmic dust acts as a protective shield for infant worlds, a catalyst for the complex chemistry of life, a regulator of galactic star formation, and even a guide for our most precise cosmological measurements. It is the invisible architect shaping everything from the smallest planetary system to the largest structures in the cosmos, a constant thread weaving through the grand tapestry of space and time. These insights profoundly redefine our place in the universe, reminding us that true power isn't always found in the brilliant glare of a star or the terrifying pull of a black hole, but often in the collective influence of countless microscopic particles, each one a silent witness to the cycles of creation and destruction. It's a humbling and beautiful truth that the most fundamental processes driving cosmic evolution rely on elements so small we would overlook them entirely if we didn't know to look deeper. This journey changes your perspective forever. The next time you gaze up at the night sky, you won't just see the bright pinpricks of stars and the faint smear of distant galaxies. You'll sense the invisible presence of the dust that connects them all. You'll know that within the dark lanes cutting across the Milky Way, within the very void between the stars, resides the raw material of new suns and new worlds. It's a reminder that we are not just observers of the cosmos, but an intimate part of its ongoing story. The iron in our blood, the calcium in our bones, and the silicon in the rocks beneath our feet were all forged in the hearts of long-dead stars and delivered to our nascent planet on the backs of cosmic dust grains. We are, as Carl Sagan so poetically noted, made of star stuff, and so much of that stuff is dust. It's a connection that ties our very existence to the most distant nebula and the earliest moments of the universe. I'd love to hear which of these 28 ways surprised you the most, or if you look at the night sky a little differently now, share your thoughts in the comments below. If you enjoyed this deep dive into the hidden forces shaping our universe, make sure to subscribe and hit the bell so you don't miss our next adventure into the wonders of space. Thank you for watching.